for my side.
Good afternoon, everybody. Welcome to this mathematical physics talk at the ICM, the second one. And we have a prominent speaker that I briefly present to you, Jan-Philipp Solovej from Copenhagen. Jan-Philipp Solovej has received an ERC grant, and he's a recipient of the Poincaré Prize. And now he will tell us about the ground state of quantum gases. Please, Jan-Philipp, the floor is yours.
So welcome back to the afternoon session. So it's a great pleasure to introduce the next speaker, Jan-Philipp Solovej from the University of Copenhagen. So he will tell us about the ground state of quantum gases. Please.
Thanks a lot. So let me thank the organizers of the ICM for inviting me to give an ICM talk, and the organizers of the Probability and Mathematical Physics for inviting me here and allowing me to give the ICM talk live in front of this wonderful audience. So I will talk about joint work with Søren Fournier from Aarhus University on quantum gases. So, well, I will tell you what a quantum gas is, a gas interacting with two-body Hamiltonians, and I will be looking at the situation where I'm in the thermodynamic limit. So I'll explain to you what the thermodynamic limit is, and then I will talk about in particular what's called the two-particle scattering length, because that is what's going to govern the situation that I'm interested in. And although I will start out by talking about quantum gases in general, I will focus on Bose gases. So this talk will focus on Bose gases, and there should have been a G there. I want to talk about the bosonic ground state energy in the dilute limit, and in particular in d equal to 3, but I will review what we now know in d equal to 1, 2, and 3 dimensions. So I will give you our rigorous results, and in fact, these results have some of them been experimentally verified, so I'll also give you the experimental verification. It was even done 10 years before we could prove it rigorously. Then I will explain where it all comes from. How do we understand these dilute Bose gases? And it goes back to what's called the Bogolubov approximation, which is the Bogolubov theory of superfluidity from 1947. So by understanding the ground state of Bose gases to the accuracy that I will explain to you, we are to a certain extent validating the Bogolubov theory from 1947. I'm not claiming that we can understand superfluidity, we can understand certain aspects of the theory. I will explain it to you very briefly, the theory and what it meant by diagonalizing the Bogolubov Hamiltonian, and what aspect of that it is that we can verify today and what is still open. I will explain how the Bogolubov approximation leads us to what I call LHY, which is the Li-Huang-Yang formula, which is the formula that's the main thing I want to prove today. And I will, on one slide, give you the rigorous argument. So up to here, I will basically talk about the heuristics, what is the idea behind it, and then I'll give you an indication of how to do it rigorously. And I'll conclude and give you some open problems. So here it is. It's the simplest, or most fundamental rather, because it's not simple, but it's the most fundamental quantum system you can imagine. It's a translation invariant problem where you have a kinetic energy of the particles represented by minus the Laplacian. I've set all the physical constants, h bar and the mass equal to, well, h bar is set to be 1, and 2 times the mass has been set to be 1. And I have an interaction potential, which is translation invariant. And this potential in what I will be discussing, this two-body potential, can be very general. So all I'm assuming about it is that it's a positive object. It can even take on the value infinity. It's spherically symmetric, and for this talk, I will assume it's compactly supported. That's not needed, but things will be more complicated if I don't assume it. So in particular, I can be looking at this very special case of the hard sphere potential, where the particles have infinite energy if they have distance less than a from each other, and zero energy, potential energy, if a distance bigger than a from each other. Basically saying that they cannot come closer than a from each other. And what I'm interested in is either fermions or bosons. So in the bosonic case, so this omega, maybe I should go back, this omega L is a box of size L. And as I said, I'm in 1, 2, or 3 dimensions. And the boundary conditions are not really important. I've written here Dirichlet or periodic, doesn't matter, because I will, in a moment, take the thermodynamic limit where I let the box size L go to infinity, and then it will be independent of boundary conditions. So this box, omega L, I'm looking at the L2 space over omega L, and I'm doing the symmetric tensor product. That is the bosonic space. I have n particles, and I do a symmetric tensor product. If I want to do fermions, and then with fermions I'm decorating it with a little f, then I do the antisymmetric tensor product. And for fermions, I'm allowing that they can also have spin, so they can take values spin j, but I will not really be discussing fermions. I just wanted to point out that one can look at that too, and there are lots of open problems for fermions. I'm mostly interested in bosons. For bosons, you may also just take the full space. You do not need actually to restrict to the symmetric tensor product, because since I will be looking only at the ground state, ground state on the huge space omega L to the n is actually attained on the symmetric subspace. But when we think bosons, we think of the symmetric subspace. And as I said, I'm interested in the ground state energy, so that's the infimum of the spectrum. Or for fermions, I would decorate it with an F. But I am interested in the thermodynamic limit. So I'm interested in letting L go to infinity, keeping the density of particles, n divided by the volume, or I could say keep it fixed, or that it converges to some value, rho. So proving that this limit here, and the limit is of not the energy itself, but the energy density, the energy per volume. So I calculate the energy itself would grow with the volume, so when I divide by the volume, I get a quantity which actually will have a limit as I let the box size go to infinity. This is a fairly standard argument, so this is the object I'm looking at. The energy density as a function of particle density. Of course, it depends on the two-body potential, but that's the only thing it depends on. And what is it that I am interested in? I'm interested in the dilute limit. The limit when the number of particles is small per volume. But this has to be expressed in some dimensionless sense. I mean, I cannot just say a few particles per volume. It has to be expressed in terms of something. And the relevant quantity is what's called the scattering length. So let me just explain briefly what the scattering length is for a two-body potential. You simply solve this one-body Schrödinger equation minus Laplacian u. You're looking for u plus 1/2 v of u. This 1/2 comes from the fact that you really study two-body scattering. So you have like two particles. And the two particles, you think of one of them, you remove the center of mass, and then the zero energy equation is this equation here. And at infinity, since v has compact support, at infinity, this is just saying that the function is harmonic outside the support. So here I'm writing down that the solution I'm looking at should be spherically symmetric, so these are the possibilities I have. And you see I'm expanding, so in one dimension it's absolute value x minus some constant, where this constant will depend on the potential v, and that's what we call the scattering length in one dimension. In two dimensions, it's a logarithm. There's again an a, the scattering length. And in 3 dimensions, there's an A again that will describe sort of the length scale of the potential. So that's what we call the scattering length. And down here, I'm saying what I'm actually looking at. The diluteness is measured in terms of the diluteness parameter, rho a to the d. This is essentially saying how many particles I have within a ball of radius a. And we would like this to be small. This is a dimensionless quantity, rho a to the d, and we would like it to be much less than 1. I put an absolute value here because a can in fact be negative if we're in 1 dimension. In 2 and 3 dimensions it will be positive, but in 1 dimension it can actually be negative. Let me just go back to the definition of the scattering length. This is what I was giving there. But there's another way to express the scattering length, and I'm doing this now only in 3 dimensions. If I look at just 2 particles and ask for the energy of 2 particles, it sounds obvious that it should be related to this equation here, and indeed it is. The energy in a box of volume L for 2 particles is 8 pi a divided by the volume, so it goes like 1 over a length squared. That's the dimension of an energy. And this is the right answer to little o, at least as L goes to infinity. So the scattering length can also be expressed as giving us the energy of 2 particles. So that will be important in a moment, in fact, right now, because I would like to understand the dilute case. And think of this gas of particles that is very dilute. So you would imagine when it's dilute that only pairs of particles see each other at a time. So you would expect that the energy is actually the number of pairs times the energy of 2 particles per volume. Now this is actually going to be the right answer in 3 dimensions. It's not correct in 1 and 2 dimensions, because in 1 and 2 dimensions the scattering solution became rather big at infinity, and actually the effect of the scattering will be very, very long range. But in 3 dimensions, that's not the case, and in 3 dimensions, this heuristics will turn out to be right. It's the number of pairs times the energy of 2 particles. And if you remember what I just told you before, that the number of the energy for 2 particles could be expressed in terms of the scattering length, you end up with the fact that the energy should be 4 pi rho squared times a, to some leading order. So this heuristics actually goes back to Lenz in 1927, and the first to try to attack it rigorously was Freeman Dyson, who proved it as an upper bound in 1957. He proved that this is the correct upper bound to leading order. He proved that in 1957. The lower bound took another 40 years and was proved in 1998 by Lieb and Ingwerson. I mean, the argument was very convincing, I hope, but it was actually quite difficult to prove. In 1947, and I think this is what prompted Dyson to look at the problem, Li, Huang, and Yang proved the paper. This is the Li and Yang from the Li-Yang theorem or the Li-Yang Nobel Prize, which was also in 1957, by the way, but not for this result. They studied the Bose gas, and they arrived at a formula for the Bose gas. And actually, the Dyson paper is in the same issue of Physical Review as the Li, Huang, Yang paper. They claim that not only is this 4 pi rho squared a the leading term, they tell us what the next term should be. So the 4 pi rho squared a was the leading term, and we have this correction, which is now known as the Li-Huang-Yang correction. And you see the diluteness parameter in 3 dimensions, rho a cubed. So there is a correction that goes like the square root of rho a cubed, and with a term which is lower order. So this has been something that has been studied essentially ever since. And I want to report the proof of that formula in 3 dimensions. And let me just already here say that there are relevant length scales for the problem. There's the length scale of the leading term, if you want, which is essentially the scattering length, A. The length scale relevant for this is what's called the healing length, and the healing length is rho a to the minus 1/2. It's easy to see that that has the dimension of a length. And here I have the relevant length scales written down. There's the scattering length. Rho minus 1/3 is the interparticle spacing. A is much less than the interparticle spacing. That's the diluteness criterion. And the interparticle spacing is much less than the healing length. So at the scale of the healing length, you see many particles. Nevertheless, the formula here, the correction, depends only on the scattering length. And therefore, it's often referred to in the physics literature as the universal formula. Universal because both the leading term and the correction depends only on the scattering length. And this is a bit surprising and has actually been one of the struggles understanding rigorously why this is the case. So here is what we know. So I have discussed now this Li-Huang-Yang formula, which is the three-dimensional case, but we actually have a very satisfactory picture now that we know the dilute asymptotics of the Bose-gas ground state energy in 1, 2, and 3 dimensions. So the thing I just tried to discuss, the history behind, was the Li-Huang-Yang formula. This is dimension equal to 3. The lower bound was proved by Fournet and myself in 2 papers in 2020 and 2021. The 2021 paper extended to the hard sphere case. The upper bound actually cannot yet be done for the hard sphere. It requires the potential to be L3. It was originally proved by Yao and Yin in 2009. They needed a stronger condition than the L3, but Basti, Senancempo, and Schlein in 2021 extended it to L3 potentials. But as I just said, it is not known for the hard sphere. In 2 dimensions, there was just a paper. I mean, literally, it's just out of the oven. It came out 2 weeks ago on the archive that does the case of dimension 2. I was not involved in this, but my collaborator Fournet and his group proved what corresponds to the Li-Huang-Yang formula in 2 dimensions. They followed very much the method that we had developed in 3 dimensions, and you see it there. Y is a small parameter. Rho A squared is the diluteness. Log rho A squared is big. We do the inverse, so Y is a small parameter. The leading term goes like rho squared Y. And then there is a Y log Y term. And then there is a term which is proportional to Y. With a constant, their gamma is Euler's constant and a constant right there. In 1 dimension, we also know the answer now. This is also from 2022, which was work I did with Ayer-Skov and Roivers. And you see again that there is now the leading term is pi squared over 3 rho cubed, and we have a correction that's linear in the scattering length in 1 dimension. So it's very satisfactory. We now know in 1, 2, and 3 dimensions how the energy behaves, at least to leading order. Here it's the first leading order, depending on the scattering length in all 3 cases. There's been a lot of other work over this is just the recent work over the years. I'm just mentioning some of the names here. Okay, so let me talk a little bit about the experimental verification. So the experiment was done. It was done, and so you might say, when do we have bosons? When do we have fermions? How can we model them? Well, you do cold atomic gases. So you think of atoms. Atoms, of course, have structure, but if you're in a system where you have a gas of atoms that's very dilute, then you can think of the gas of atoms as being a gas of particles. And depending on how many fermions make up your atoms, you count the electrons, the neutrons, and the protons, then the atom may actually behave like a boson. So 7 lithium, this particular type of lithium, is a boson. And physicists have a way of regulating the way they interact. They have this they call the Feshbach resonance, so putting it in magnetic fields. They can adjust the interactions of these particles. In particular, they can adjust the scattering length. So I have 2 cases here. One when the scattering length is 1,400 times the Bohr radius and 2,150 times the Bohr radius of the same atom, 7 lithium, but in a different experimental setup. So the experimental setup is here. It's a cylindrical trap, and I put the dimensions there. So the length of the system is 100 micron, but the diameter of the cylinder is only 5 micron. It's dilute. Its rho A cubed is essentially 1/1000, so that's fine. And the healing length is about 1 micron. 1 micron is not so far from 5 microns, so one might argue that we're not really in the thermodynamic limit because the healing length was the relevant length scale. It would have been nice if the healing length was much smaller than the perpendicular radius. But anyway, that's what we find. And what is plotted here is what's called the pressure. It's the Legendre transform of the formula I gave you for the energy. It again has these famous 128/15 square root of pi. They measure it, and they measure the 128/15 square root of pi. 128/15 square root of pi is 4.81. They measure it to be 4.5 plus minus 0.7, so the accuracy is not so good, but it agrees quite well with the theoretical number. It would have been nice if there had been more data than just 2, but I guess the experiments are difficult to do. I'm not an expert at all. So let me say a little bit about the Bogolubov approximation. I'm not going to teach you the theory of superfluidity at this point, but I want to indicate some of the ideas, and my goal is to show where the 128/15 square root of pi comes from. So what does Bogolubov say? Well, he says that there are 2 assumptions in the Bogolubov approximation that's behind his theory of superfluidity. So you should think of it in this way. So in this big box, the universal box, the thing that I'm going to let go to infinity, imagine for a moment that I think of periodic boundary conditions. I know I told you that boundary conditions are not important, and they will not be. But for the discussion I want to give you right now, I will assume periodic boundary conditions. And then think of, in this space, L2, the one particle space, the square integrable function on this box. Let's divide it into the space of constant functions and everything that's orthogonal to constant functions. So the projection onto constant functions I will call P, and the projection orthogonal to constant functions I will call Q. The first thing in Bogolubov's approximation, step 1, is the assumption of condensation. And that is that most particles are in the constant function. I mean, are occupying the one particle state corresponding to the constant function. Well, let me try to say this a little more precisely. In fact, let me think of the particle number n. N is, well, you can think of it as 1 summed from 1 to n. Right, the identity, think of it as the operator, which is the identity summed over the n particles. But the identity I can write as P plus Q, right, because P and Q are orthogonal projections. So I can write the number operator, which is a fixed number in everything I'm discussing at this point. This is some number, but I can write this number as a sum of 2 operators. The sum over the PIs, which are the projections onto the constant functions, and the sum orthogonal to the Pi, to the Qi. So the Q I will refer to as the excited particles, those that are not in the condensate, and the Pi's, and those that are in the condensate. So I'm writing these 2 numbers, n0 and n plus. N0 is this operator. I call them numbers, they're really operators. N0 is this operator, n plus is that operator. They sum to a number, n. But they are themselves operators and they fluctuate. So they don't have a fixed value in the ground state. The Hamiltonian does not commute with n0 and n plus. Bogolubov's approximation, the condensation assumption, is saying that the operator n0 is essentially n. Almost all the particles are in the condensate. So we can just as well replace the operator n0 by n. So that's what Bogolubov does. Of course, that's a rather strong thing to do, and one has to explain how that's true when you do the rigorous the rigorous understanding. Because of course you might say, well, but then n plus is 0. No, but that's not how we think about it. n0 is almost n, but we're still going to talk about the fluctuations in n plus. And then the next thing is, since n plus is small, Bogolubov does the following thing. He didn't express it this way that I'm doing here, but I'll try to explain it to you by not going to second quantization for a long time, but at some point I will have to go to second quantization. But for now, let me not do it. The potential V was a two-body potential, right? So it was V of xi minus xj. So it actually acts on two particles. So it acts on the two-particle Hilbert space. In the two-particle Hilbert space, I have the identity tensor the identity. The identity for one particle tensor the identity for the other particle. And I write the identity as P plus Q, right? The projection onto P and the projection onto Q. So I have P plus Q and P plus Q. And I do the same on the other side of the potential V. V commutes with the identity, but it's not going to commute with P and Q. So when I take and write it like this, write the V in this way, I can now expand out all these sums, and I get 16 terms. Right? The first term is P tensor P, V P tensor P. That's what's happening in the condensate. Then I get a term that has, well, I mean, I didn't write all the 16. I wrote the first one and the last one. The last one is the one that has 4 Q's in it. Q tensor Q, V, Q tensor Q. One observation that comes from having periodic boundary conditions is that there are no terms with just one Q. Because there's momentum conservation. So if you have P, P, V, P, Q, that cannot happen because the P corresponds to momentum 0, so you have to have the same momentum coming in as going out. So there will be no terms with one Q. There are terms with 2 Qs, 3 Qs, and 4 Qs. But then Bogolubov says, well, but the Q is small. I was telling you n plus is 0. So when there are 3 and 4 Qs, let's just ignore it. So he says, let's ignore 3 and 4 Qs. And then you are left with something that has only 2 Qs or no Qs. The thing with no Qs is this one, and then all other terms with just 2 Qs. So let me tell you how to deal with Hamiltonians if we have done exactly what Bogolubov prescribed, and we are ending up with something that has only 2 Qs in it. It's actually very, very simple. So here it is. But it's easiest to see it in second quantization. So here's a term with 2 Qs, Q tensor Q, V, P tensor P. I mean, I'm just giving you sort of the flavor of it. You really have to write it down. It's, of course, a little bit more complicated, but it's really just algebra in a sense. You think of writing this, think of this as an operation that kills 2 particles in the condensate and creates 2 particles out of the condensate in the excited particles. So if I introduce second quantization, creation and annihilation of particles, I would be creating 2 particles, A star, A star, out of the condensate. Momentum conservation tells me that I create one with momentum P and one with momentum minus P. So I can think of this term being of that form. I also have terms that have Q's on both sides of the V, so P tensor Q, V, P tensor Q, and those terms annihilate something out of the condensate and create it out of the condensate again. So this would be of the form A star P, AP. So you can actually write down the whole Hamiltonian in terms of, for each momentum P, operators of that form, A star P, AP, and A star P, A star minus P. So let me just symbolically write this down and tell you basically how you would diagonalize such an operator, and that's incredibly simple. So here I'm written it by just calling this the P, I'm calling plus, and the minus P I'm calling minus. So I have terms here, A star plus, A star minus, A minus, and then I have A star plus, A star minus, A plus, A minus, because I also have the term when the Q's are on the other side. So my Hamiltonian will look like sums over momenta of operators looking like this. And these operators, plus and minus, they commute with each other. And now I say, well, but this is a quadratic expression. Let me just complete the square. So I simply complete a square here. So I'm going to write it in terms as something b plus star b plus b minus star b minus. And I'm writing down here exactly what you do. I mean, this calculation is completely trivial. It's just completing a square. I have these new operators. And if these operators were bosonic, those will in fact also be bosonic up to a normalization. And the important thing is that I get a correction term which has to do with the commutator of A plus with A plus star and A minus with A minus star. There's nothing, I'm not assuming anything about bosonic operators at this point. I'm simply saying if you have two operators that commute, this expression can be rewritten like that. If they're bosonic, then this would be a 1, and that would be a 1, and this would be the ground state energy. So in fact, we expect that the ground state energy is of this form, something with a constant A here and the square root A squared minus B squared. I want to say two things about that formula. If you actually write it down in terms of momentum, then this will be a positive operator. So for the ground state, and you can and you expect this one to have energy 0, so that this will actually be the ground state energy. This does not follow from this simple lemma, but that's the motivation behind it. Now, when you actually do the calculation here, so let me go over to the board and just show you there's this D, and there's the famous picture that Bogolubov found, that this function D here, when you calculate as a function of momentum, it actually looks like this. So it has a dispersion law that's linear. And that is the explanation that actually Landau then had already given before Bogolubov, that if you have a dispersion law like this that's linear, then you would have superfluidity. If your velocity is so weak that it does not excite these particles, meaning that the slope, that it's smaller than that slope, then you're below what's called the Landau critical velocity. What Bogolubov did was actually to explain where this linear dispersion law came from. It comes from this D when you actually plug in all the dependence on the momentum. We cannot prove that this is correct in any way. We are aiming at proving that this is the correct expression for the ground state energy. So let me give you the formula that you would get to. And again, this is just to give you an idea of how you are getting to this Li Huang-Yang expression from Bogolubov theory of superfluidity. So all I want you to is sort of have a feeling for it, some number minus the square root of the number squared by minus some other number squared. And oops, that was the wrong way. And you should recognize exactly that this expression looks like that. I'm not giving you the details, what was the A, what was the B, but if you plug it in, do the calculation, that's more or less the integral you will end up with. I'll get back to it in a second, that I've made a little approximation already to get to this formula. There was a first term, forget the red terms for a second. The 4 pi rho squared A0 is actually what you get from the PPPP term. That was still there. I didn't discuss it when I discussed Bogolubov. That's sort of the 0th order term. So that gives you the 4 pi rho squared, something I call A0. A0 is 1 over 8 pi integral of the potential. Now, what I have done here in this integral, I have written down the expression, but I also took the dilute limit, meaning that here I should really have had something that was some dependence on the potential, but in the dilute limit, the only thing that occurs is the integral of the potential. So this is what you would get from Bogolubov. Unfortunately, with this approximation, the integral is divergent. If I had not replaced V of P only by v of 0. I mean, integral of v is v of, when I say v of p, I mean v hat of p. Right? So here, this is the a0 is the integral of v. There should have really been v hat of p there. The Fourier transform should have come in. If I had not done that replacing v, the Fourier transform by its value at 0, I would have got an integral that would converge. But I would like to take the dilute limit, and if I just do it formally, I end up with this integral, and this integral diverges. But what I can do is I can subtract the divergent part. I mean, I simply expand again, I subtract it, and I add it again. But I have to be careful. When I add it, I have to add it with the v hat of p dependence. So this term a1 and that thing, they cancel in the dilute limit. So this is the formula I will end up with when I use this on the Bogolubov Hamiltonian, where I ignore the pp and the qq term. But now remember what I'm aiming at. I'm aiming at proving that the leading term is 4 pi rho squared, the scattering length. And that here I'm getting something with 128 over 15 square root of pi. Okay, so let me first explain to you where this 128 over 15 square root of pi comes from. Well, that is simply from this integral. If I take this integral and simply change variables, and remember I told you that rho square root rho a was what I called the healing length. So if I do this healing length change of variables in that integral, I end up with just a regular integral, dimensionless integral, that's written right there. You recognize the different terms from up here. That integral you can do, and if you plug in all the numbers, you end up with 128 over 15 square root of pi in calculating that integral. What about the leading term up here, the a0 plus a1? a0 was 1 over 8 pi integral v, and a1 is some complicated expression there. Where do they come from? Well, in fact, and this was realized by Landau, at least for the first term, that this is an approximation to the scattering length. In fact, there's a famous approximation to the scattering length called the Born series. These are the first two terms in the Born series of the scattering length. Unfortunately, there's no one telling us that the Born series converges. In fact, if I plug in the hard sphere potential, all the terms are just infinity. I mean, this term is just infinity for the hard sphere. But if I simply replace the a0 plus a1 by the scattering length in the first term and the a0 by the scattering length in the second term, do this integral, then I end up with the Li-Huang-Yang formula. But I hope you can see that there are a lot of things one would need to rigorously justify to do this. Let me maybe just go back to one of my first slides on the scattering length, that the scattering length actually has a formula in 3 dimensions, which shows that it's always less than this 1 over 8 pi integral v. This was the first term in the Born series. This can be infinity if I have the hard sphere, but a for the hard sphere is just the radius of the hard sphere, so that's finite. And we have to understand why this actually is replaced by the a. So that was the big struggle in trying to make the formula rigorous. So let me just briefly tell you how we do this rigorously. How do we do this Bogolubov approximation rigorously? So one problem is that we have to establish condensation. This was the first step in the Bogolubov approximation. Unfortunately, this is one of the holy grails in this theory. We have no idea how to prove that there's condensation in the thermodynamic limit. That the number in the big box, that the number of particles in momentum 0 is almost all the particles. We have just no idea how to prove that. We have quite far. There's some cases where we can do it on a lattice, where the hard core gas at half filling is basically the only case where we can do it. That is certainly not a dilute. Half filling for a lattice with hard core interactions is very far from the dilute limit. So in the situation we are in here, we have no way of proving condensation. But we don't need to prove condensation, because we only need to prove condensation if we zoom in on a window of the size of the healing length, right? There's no need to prove it where the action is not going on. We're just proving it where the action goes on. So, but that requires that we localize two boxes of essentially the size of the healing length. It should have said length here. So that requires a very complicated localization technique that gives a very complicated kinetic energy in the box. Everything is being messed up. So we basically need a very robust method to be able to study when that happens in the box. It's no longer periodic. It's no longer the standard Laplacian in periodic boundary conditions. So this is really why we still have to struggle, even though we figured out how to localize and actually prove condensation on that scale. We need a very robust method to continue. And here is then what we do as the second step. Remember, the second step in Bogolubov was to ignore the 3Q and 4Q terms. That's no good. I mean, this is wrong. Bogolubov, one of the reasons Bogolubov does not get the right answer, namely the scattering length, is that you cannot ignore the terms with only 3Q and 4Q terms. You have to do something more clever. And here is what we do, which is more clever, and it's actually very basic still. It's again just completing a square, but the right square. We recall there was this scattering function. We have to get the scattering length in there. So we take the scattering function, you write it in 3 dimensions as 1 minus omega, and then what Bogolubov would do was to ignore the QQV. Here I'm omitting the tensor product, otherwise this formula would run off of the slide. So the QQV term is a positive term. So for a lower bound, I can throw it out. But that's not going to work. I will not be able to just throw that term away. It's simply too big. It's going to give contributions to even the leading order term. So we're looking for what to throw out. And here's another term that's positive. Right? The V is a positive potential. So right on the left, QQ, and then PP plus QP plus PQ times this omega, which came from the scattering length. And then the same thing on the other side. Right? So this is positive because V is positive, and I have the same operator on both sides. So we simply use this lower bound. So we add and subtract that term. And then we throw out the positive term. And we look what the negative term does to all the other terms. And it will remove the QQ term, and will sort of renormalize all the other PP, QQ, P, QQQ, and whatever. They will all be renormalized. But then you're not finished. Now you have to do Bogolubov. I told you that we had messed up the kinetic energy. We now have some very complicated terms there. Nevertheless, it turns out to be possible to do an iterated Bogolubov diagonalization. So, but essentially just the lemma I showed you before, and then arrive at the final result. So that was the proof of the Li-Huang-Yang formula. I hope I gave you an impression of where the formula came from and what is involved. I did not give you all the technical details. We ended up writing 2 papers, each of 90 pages. One that was the potentials that were not the hard sphere, and then another 90 pages just to deal with the hard sphere. But we now have what I think is a fairly satisfactory picture of the dilute Bose gas in 1, 2, and 3 dimensions. One can ask for higher order corrections. So here I'm giving you some open problems, and also some problems I didn't discuss at all, but you would like to understand higher order corrections. Are there more terms that are still universal that depend only on A? There's a conjecture that there's one more term in the dilute Bose gas that depends only on A. Of course, there's establishing Bose-Einstein condensation in the thermodynamic limit. I would hope lots of people would start working on that problem. This is, in a sense, the holy grail of many-body quantum mechanics for Bose gases, understanding why there's Bose-Einstein condensation. There's also the understanding of the high-density limit. In fact, the best thing we know goes back to Lieb from 1963 that showed that in the high-density limit, you're getting 1/2 rho squared integral V, not the scattering length, but really the integral V, minus 1/2 rho V of 0, I mean, the value of V at 0. But notice there's nothing universal about this. This depends on two properties of the potential, the value at 0 and the integral. It may be of some interest to point out that this formula actually also follows from the Bogolubov approximation. Of course, I haven't talked about fermions. I just tried to advertise in the beginning. There is also the high and low density expansions for fermions. People have started working on this for confined gases. We are still far from understanding it in the thermodynamic limit. And then there's also, what about when the temperature is positive? I was just talking about the ground state. What do we know about positive temperature? So thanks a lot for your attention. That's all I have to say.
So thanks very much, Jan-Philipp, for this beautiful talk that we have seen and the great results. And thanks for everybody to attending this seminar. As was announced in the beginning of the talk, the questions have to be asked in the Discord chat in writing to Jan-Philipp Solovej. You cannot ask it here orally, unfortunately. So rather the session, I have to close the session now, and I wish you a good afternoon and a great further conference.
Thanks a lot.